Hi ladies and gents, welcome back. We are going to be taking a look at a different kind of test here that falls under the Anova umbrella, but it's something called the Kruskal-Wallis test. Now, let's take a look on page A13 here, and I'm not going to spend a lot of time on these two pages here because I'm going to put up a lab video that tells you how to use an Anova template. And when we get there, we'll actually come back to these couple of pages. Or actually, I'm going to take you to some pages that actually flesh it out a little bit more. And just to show you where I'm going on that one here, if you go down to page, what is it? I guess it's 214 of your manual. So this is right at the end of the formulas. So here's the end of the formulas, and then you've got these kind of sideway pages here, which are for helping you to decide what kind of test to use here. And I've actually turned these a little bit, so let me just move down there for a second. We're going to go to right here. And so this is talking about when you've got two variables and you want to compare them. If it's nominal versus nominal, you've got a test of independence. And that's what we've been looking at in the last unit. In this particular unit here, so this is the Unit A stuff down here, is if you have a nominal variable and an ordinal variable, then you're going to use Kruskal-Wallis. So the Kruskal-Wallis test then is used when for questions like, what quadrant of the city do you come from? So that would be nominal in nature. And then how would you rate the quality of the roads, let's say, on a 5-point scale? And so that would be a rating system. So that's ordinal, nominal versus ordinal. You automatically go to a Kruskal-Wallis for that kind of question. But the one I want to focus in here on is nominal versus interval, which is talking about what really should be Anova, but Anova is dependent on certain conditions being met. So I'm not going to spend any more time on this particular page here. I'm going to go back here. And again, I'll have a lab video that goes through this in a little more detail and shows you an Anova template. So I'm going to go back here then to where I was. And that is about somewhere around here. So page A13, the Anova Conditions. And so it says that Anova is a powerful parametric statistical test. Now, parametric, remember, means that you're dealing typically with interval scale variables. In this case, nominal versus interval. And with interval scale variables, there tend to be conditions. And normality is one of them. In fact, when we take a look at the Anova test, there's actually 3 conditions that have to be met here. So let's take a look at them here. Number 1 is just, it's a standard kind of statement for any statistical test. So it doesn't matter whether it's Anova, it could be a test of independence, it could be just a single hypothesis test that we learned about in our first stats course, and that is that the samples are drawn randomly and each sample is independent of the other samples. So in other words, a good sample design. And so that's just kind of a standard statement. If you don't have that one, you can't really do any statistical tests. But here's the 2 I want to focus in on when we're talking about Anova. Now, number 2 is, you've seen this one actually a lot before. The populations from which the samples are drawn are normally distributed. That whole thing about the central limit theorem that we talked about way back in your first stats course, and that the condition of normality needs to hold unless the sample size is at least 30, and then the central limit theorem kicks in rather than the first limit theorem, and you're fine. So we'll be taking a look at that one. So we'll be asking, are the samples normally distributed? But this is a new one here, and that is that if they're normally distributed, then the populations from which the samples are drawn have the same variance. Okay, so what does that mean in terms of the Alberta, BC, and Ontario trees? So we had things like this, and we had the different numbers down here. What we do is we do a normality test on each of these individually. And I'm going to show you a template that does them all three at the same time, right? So they're three separate tests, but you'll just see the results, boom, 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 right there. And so it does a test then on this particular sample, and it asks, well, is that sample approximately normal? And if it is, then you're good to go. And then it asks the same about BC, and it asks the same about, sorry, this would be O for Ontario. Asks the same for Ontario. And if the normality passes in all three cases, then you have to go on and check for condition number 3, which is the whether they have the same variances. All right. If normality fails for any of the treatments, then you stop there and you immediately go to a Kruskal-Wallis test. If the N is at least 30 for a particular treatment, then you don't have to worry about it because of the central limit theorem. But if N is less than 30 and normality fails for any of the ones where N is less than 30 and normality fails, then you go to a Kruskal-Wallis test. If normality passes for all of them, then you go and test for homogeneity of variances. And we're going to be using something called a Bartlett's test for that. And that's something which you're not going to be doing by hand. It will automatically be done for you in this Anova template. So I've got a little Anova template, which I'm going to talk about in a lab. I think I actually renamed it Anova template, but you'll see that in your supplementary files folder. So it'll talk about how to go through this. This also talks a little bit about unstacking and so on, and checking the conditions in the Anova file. We're going to just set that aside here and say that a lab video is going to pick that up. So let's say that we run through that and we find that either normality fails, or if normality passes for all of the treatments, the test for homogeneity of variances fails. Then what we do is we go into here and we use something called a Kruskal-Wallis test, which is a non-parametric equivalent to the Anova test. Okay? Let me back up just a second here and say, remember in Anova, what we're doing is we are testing that the means of the treatments are equal. And yet we're using an F test, which is a ratio of variances, right? SSB, S sum of squares between, divided by sum of squares within, SSB over SSW. But in order for that to work, you actually have to have the variance of the samples have to be pretty close to each other. So you can't have one that has the numbers really widely spread out, and another one where they're really compact. So that's what what we'll call a Bartlett's test, the test of homogeneity of variance, is all about here. So we're going to get into that in a lab video, but for this, at this particular point, all I want you to note here then is that if the second or third condition fails, that is the normality fails or homogeneity of variances fails, then it means that we end up using a Kruskal-Wallis test. Okay. Also, if you have, as I mentioned, nominal versus ordinal to begin with. So if you're talking about, say, ratings, then right away you go to a Kruskal-Wallis test, because you're not testing normality, you're not testing homogeneity of variances with an ordinal variable. So it's only for the interval variable there. All right, so let's say then that your second or third Anova assumptions fails. So what we do is we go down here to the KW test here. This is actually a pretty easy test to work through. It's always done exactly the same sort of way here. You take your data, and it says that all the data are considered together here. So they might be broken down into various columns or rows, but you consider all of the numbers together. And what you're going to do is you're going to change those numbers into ranks. So the lowest number you're going to assign a 1, and then the next lowest number you're going to assign a 2, and so on like that. If you have two or more numbers which are exactly the same, then you give them an average rank, and we'll see an example of that. So that's what number 3 is about here. And then number 4, it says the sum of the ranks must equal nt times nt plus 1 divided by 2. By the way, this is not like the check that we do when we are doing a normal approximation of the binomial. Can we use a z-test for a binomial type problem? It's not the same sort of thing. This is just simply a mathematical check to see if you did your ranking correctly by hand. That's all it is. And it goes back to high school where you talked about the sum of the numbers from 1 to n. And so that's where you've actually seen that formula before. So it's just a real quick and dirty check to see if your numbers were done right. But let's get into the actual steps of the hypothesis here. So if we were talking about ANOVA, of course, we're talking about the means are equal. So in the tree example, we had that the mean of Alberta trees is equal to the mean of BC trees is equal to the mean of Ontario trees. When we change the numbers into ranks, then now we're going to be testing medians. So the median of Alberta trees is equal to the median of BC trees is equal to the median of Ontario trees, against the alternative that at least one of the medians differs from the others. So all we're doing is we're testing medians instead of means. The test statistic is actually a chi-square statistic. So chi-square star is equal to this. It looks a little goofy, but you've seen just about all of these symbols before. By the way, the W is just something which is used in a lot of stats books to represent Kruskal-Wallis, obviously the W from Wallis there. And that's because K is used a lot in stats, and so they don't call it the K test. So sometimes you'll see that just called the W test there. But it's we're just going to call it the chi-square star is equal to these numbers here. Now you've seen NT before, and the NJ, is just the N for the jth treatment, and then this is the sum of the rankings. And so we'll go through and take a look at that. The rejection region is always an upper tail chi-square test. All right, with K minus 1 degrees of freedom, where K is the number of treatments. And then calculate your test statistic and then your decision. So let's run through an example here. All right, so it says number 5 here on page A16. This problem does appear in the problem at the back, but there you're only asked to solve it as a one-way ANOVA problem, so you can certainly take a look at that. A firm wishes to compare 4 programs, so the programs, of course, are nominal, right? Program 1, 2, 3, and 4. 4 training workers to perform a certain task. 20 new employees are randomly assigned to the training programs, 5 in each program. At the end of the training period, a test is conducted to see how quickly trainees can perform the task. So we're talking about the number of times the task is performed per minute is recorded. Now, that is obviously an interval variable. So nominal versus interval means that we should be using ANOVA, right? And in fact, I ask you to do this as an ANOVA problem in the additional problems at the back of this unit. Why would we use a KW test? Well, if we put it into the ANOVA template, we might find that either normality fails or that the homogeneity of variance test fails. So if we go into the ANOVA template, which again we'll see in a lab video, it will actually do a normality test for each of the programs here. Now, none of these have an N of at least 30, so we would have to take a look at what the normality test says, and it's something called an Anderson-Darling test. We'll see in the lab video. And if you reject HO for any of those, then we immediately go to a Kruskal-Wallis test. If normality passes for all of them, so in the Anderson-Darling test, if you accept HO, then for all four of them, then you go to the Bartlett's homogeneity of variance tab and see if that passes. And if that's rejected, then you go to Kruskal-Wallis, and if that's okay, then you would go to just the Anova test. So obviously you want to watch this particular video and take a look at the lab video as well and see how that template works. But let's say either normality fails or the homogeneity of variance fails. And so we have to end up using a Kruskal-Wallis test. So what we do is we go through here and let me just get rid of some of the things here, clean it up a little bit. Okay, so what we do is we go through here and we look at all 20 numbers together. Ignore the fact that they are broken up into 4 different treatments. So just think of them as 20 numbers. And you find the smallest one, and you assign it a value 1. So the smallest number is a 6, and so it is assigned a 1 here. By the way, I'm just going to write down the 6 here. You'll see a little bit later why I'm doing that. The next number here is a 7, and so that is a 2. And then the next one is an 8, and we've got, let's see, I think we've got a couple of those, yeah. So what we've got here is 2 8s. I'm just going to write them down here. And the numbers that we assign here, maybe I should have put those in a different color here. Yeah, let me just change the color here for a sec here. So we've got a 6, 7, 8, 8, and we're going to find that there's 4 9s, there's 2 10s, and then there's 4 11s, and so on like that, okay? So what we do is we say, okay, smallest number is a 6, we assign it a 1. Second smallest number is a 7, so we assign it a 2. Now what we have is we have a tie for the 3rd and 4th positions. So what we do is we assign them a 3.5 each, which is the average ranking of those two. So the 8s become a 3.5 and a 3.5. Now we've got 4 9s here. And so the 4 9s then, they would be 1, 2, 3, 4. This would be the 5th, 6th, 7th, and 8th values. And of course, you can't distinguish between those, so what you do is you average them. So 5 plus 6 plus 7 plus 8 divided by 4 gives you 6.5 is going to be the average ranking that we have there. Okay, and so that becomes then 6.5, 6.5, 6.5, and 6.5. Now we come to the 10s, and they would hold, we're up to, let's see, 5, 6, 7, 8. We're up to the 9th and 10th numbers. They're equal, and so we would give them 9.5s. So we've got 9.5, and where's the other 10? 9.5 here, like that. Now we've got 4 11s, and they hold the, let's see, we're up to 10, we're up to 11, 12, 13, and 14. So 11, 12, 13, and 14 as the ranks. You add them up, divide by 4, and you would get 12.5. So they're all going to be 12.5s. So where's my 11s? 12.5, 12.5, oops, 12.5, and 12.5. Okay, I'm not going to write any more down here at the bottom. But let's see, what do we got next? We've got the 11s, we've got the 12s. I think there is 2 of those. So we're up to, let's see, 11, 12, 13, 14. We're up to the 15 and 16th numbers. So there's 2 of these, so we're going to give them 15.5 for the 12s. 15, 16, we're up to the 17th and 18th numbers because there's two 13s. So they're going to be 17 and a halves, 17, 18, and then we're up to 19 and 20, and those are the two 14s. So 19 and a half is the average rank of those. So that's what you do. Of course, if you had three numbers, then of course it would be, let's say they're the 5th, 6th, and 7th, just 5 plus 6 plus 7 divided by 3 gives you an average ranking of 6, that sort of thing. So that's how you do that, and I'm just going to really quickly check my numbers here to make sure that they look good. Now, what you do is you add up the ranks for each of the treatments. And so if you add these guys up across the green ones for program 1, you are going to get 71 and a half. And then for program 2, it comes to 33. And then for program 3, we've got 77 and a half. And then for program 4, we've got 28. And just as a quick check then, that adds up to 210, and that should be equal to NT times NT plus 1 divided by 2. So your total N is 20 times 21 divided by 2, and that should give you 210. All right? So these are your RJs. These guys right here. So the sum of the ranks for each of the programs. All right, now that we've done that, the rest is pretty simple. What we do is we go in here and we say, all right, step number 1, our HO. This is actually part of step number 4. So I'm kind of jumping ahead of myself. So let's go back and clean this up now, because we want to put down our HO and our HA, which is the medium of program 1 is equal to the median of program 2, program 3, and program 4. Against the alternative, not that they're all different, but at least one of the medians differs. All right. Step number 2 is where you have that goofy kind of formula here, which looks like this. It's been a while since I've actually done one of these. So it's 12 over NT times NT plus 1, and then times the sum of the RJ squares over their NJ. And here I'll put some kind of square brackets around that just to further divide them out. Minus 3 times NT plus 1. So it's kind of a goofy formula, but that's what the thing looks like. Step number 3, this is always an upper tail chi-square test with k minus 1 degrees of freedom. Now, k minus 1 is the number of treatments, and so we've got 4 minus 1 will give you 3. Does it say anything in here about an alpha? No, so we'll assume an alpha here of 5%, and so we're going to have our 5% here, always an upper tail chi-square distribution. And so that is that. Let's go down to our table here for chi-square. We're looking at 3 degrees of freedom, always upper tail chi-square, so it's going to be 7.81. Right there. All right, so 7.81, and of course, if you want to write that as a statement, you would say if your chi-square star is greater than 7.81, then you would reject HO. All right, I've already started 4 here, which is the calculation. So now we're going to continue with that, and we're going to plug this into the formula and say this will be 12 divided by NT. NT is you've got 20 numbers in total times NT plus 1. And then we've got, let's see, so the first RJ is 71.5 squared, and then divide it by 5, which is its n. Now the n's can be different, of course, in another problem, but these are all 5. And then we've got 33 squared over 5. I'm going to run out of room here. 77.5 squared over 5, and 28 squared over 5, and this is still part of the formula here, minus 3 times 21, so minus 3 times NT plus 1. And when the smoke clears on that one, you're going to get, what do you get here, 11.24. So 11.24, of course, falls right in here. And so what we would say then is 11.24 is greater than 7.81. Therefore, we're going to reject HO. And then you want to describe the differences. And what we'll see here then is we're not going to do the equivalent of a Fisher's comparison. That requires that it's interval scale variables. But what we'll see here is that these two are actually pretty similar, and then these two are pretty similar here. And so I would say, in terms of just describing the relationship here then, that program 1 and program 2 have higher medians, than, that's program 1 and 3, than program 2 and program 4. Okay, so that was 1 and 3. And then versus 2 and 4. And that's how we do the Kruskal-Wallis test. Again, there's a template that will help you with that much easier. But I do want you to know how to do this by hand. For homework, I would like you to do number 6 on page A17. You'll notice that the n's are different in this particular case. They're not all 5. And that's where we'll end the lesson. Thanks for listening.